Okay, hi, good evening. Yeah.
Hello, good evening.
Yeah. Okay, so today I think we'll be solving some questions from chemical kinetics, and let's say if time permits, we'll discuss some topics from fluorescence, phosphorescence also. Okay, let me just share my screen. Just a second. Okay, so here it is said that the time constant tau is the required for the concentration of a reactant to fall to 1 upon E of its initial value. So this question is for first order reaction. Actually, we know that for first order reaction, so let's say reactant to product, A is the reactant and P is the product, and rate of the reaction, which is the minus dA dt. This is the rate of the reaction, which would be equal to some rate constant K times, so concentration of A to the power 1, so that means it is first order. So if you just integrate this, you will get like A of T equal to A0 times exponential minus K tau, right? Now you will get, so K tau will be ln of A0 divided by AT, right? So here it is mentioned that we have to just find out the K value of K tau, and here it is mentioned the concentration of the reactant at time t, let's say AT, to fall to 1 upon E of its initial value. So AT, which will be equal to 1 upon E times initial concentration A0, right? So you can just put it here, K tau, which will be equal to ln initial concentration A0 divided by AT, which will be just E times A0, right? So A0 will cancel, so K tau will be ln of E. So ln is basically E based, so ln means log of E based, right? So the K tau will be equal to 1 for this case. So actually, to solve this question, you have to just remember for first order reaction how the rate equation appear. So first order reaction minus dA dt, that means rate of disappearance of reactant, which will be equal to just rate constant times the concentration of reactant to the power 1. Now you can just integrate this. So the rate equation will be A at time t, concentration of A at time t, which will be equal to concentration of A at time 0 times exponential minus k tau. This is for first order reaction. Okay. What is happening? So the second question says the percent transmittance of a solution having absorbance, which is basically the optical density, 1 is. So we have to just find out the percent transmittance of a solution having absorbance. So absorbance value is given and we have to find out the transmittance value. Okay. So basically this question is from spectroscopy. Now in spectroscopy, in a cell containing solution, so basically we just pass light through this cell containing solutions, and we then measure the absorbance value, how much light is absorbed by the solutions, and then the amount of light emitted. Like, so we pass light here, then we just calculate the absorbance at different wavelength. Then the amount of light emitted is called the transmittance. So basically the relationship between the percent transmittance and the absorbance is A equal to minus log T. Log is basically 10 based, log 10T. So here A is absorbance and T is transmittance. So we have to find out the T here. So T will be equal to, so 10 to the power minus A, right? 10 to the power A is given, A is 1 here, so 10 to the power minus 1. So T equal to 1 upon 10 equal to 0.1. So transmittance value is 0.1. So percent transmittance will be just 10%, right? So transmittance is 0.1%. Transmittance will be just 0.1 times 100%, which will be equal to 10%. Okay, so the main relationship is A equal to minus log 10 base T. So this is the important relationship, and there is another formula here. So absorbance A equal to epsilon CL. So epsilon is actually molar extinction coefficient. So this is a constant, and C is concentration of which? Concentration of any particular salt in solutions concentration, and L is the path length of the cell, path length. So let's say this is cell, so this is L, path length, and the concentration of this solution is C. Let's say C mole per liter. Then the absorbance will be epsilon times concentration of the solution times path length. Okay, so just remember this formula, it will be needed. So third question says, and a catalyst increases the rate of chemical reaction by increasing the activation energy. Second option is decreasing the activation energy, and third option is increasing the average kinetic energy of the molecule. Fourth is the increasing the number of active molecules. So what do you think which should be the answer?
One and four, D option.
1 and 4. If you increase the activation energy, then the rate of the reaction will decrease, right? So if you remember this picture, so this is reactant, this is product. So activation energy is the energy difference between these two, transition state and reactant. So if you increase the activation energy, that means if you increase this gap, so then the rate of the reaction will decrease, right? Okay, so I think A 2 and 4, yeah. So basically 2, just a second, yeah. So catalyst basically, so catalyst actually increases the rate of the reaction, right? So basically rate of the reaction increasing means, so the activation energy is decreasing, that's why the rate of the reaction is increasing. So the decreasing the activation energy is definitely the correct answer, but so option 2 is not the only correct answer. So the third option is increasing the average kinetic energy of the molecule, and it is not true. And increasing the number of active molecules, yeah, number of active molecules obviously increasing because of the presence of catalyst. So the correct option will be option A, basically 2 and 4. Got it? Is it clear now, Shika? I think you have.
Yes, sir. I was wrong.
Yeah. So basically catalyst decreases the activation energy, this gap. So if you just draw another picture, this was previous, like without catalyst, this is activation energy EA, and if you draw another picture, and this is in presence of catalyst. So catalyst basically decreases the activation energy EA prime, let's say. So EA prime is less than of EA. By stabilizing the transition state, so this was the transition state. So any catalysis, it could be enzyme catalysis or any acid base catalysis. So catalysis actually stabilizes the transition state or activated complex. That's how it actually decreases the activation energy. That is the energy gap between the activated complex and the reactant molecules, and by which the reaction rate increases. Okay, so for the following sequential reaction, so it is a kind of sequential, it is not the sequential reaction, so it is wrong actually, it is a parallel reaction, right? So sequential or consecutive reaction means A to B, then B to C, right? So we have seen that in the previous classes. So let's say A to B with rate constant K1 and B to C with rate constant K2. So this is kind of consecutive or sequential reaction. But from A to B and then from A to C, so this is a kind of parallel reaction. So K1, K2. So this example is from parallel reaction. So for the following reaction, A to B with rate constant K, so let's say Ka and Kb, time at which the B time at which B maximum is. So basically for parallel reaction, we have seen the plots, how the plots were. At which the B maxima is. Okay. This picture is wrong actually. Like, okay, let's say for sequential reaction, take A to B, then B to C, right? So let's say this is Ka and this is Kb. So this is a kind of sequential or consecutive reaction. So at first, at t equal to 0, the initial concentration of A was A0, right? And there was no B and no C. But at time t, so the concentration of A will decrease, and with rate constant Ka, the constant B molecules will form, and after that with rate constant Kb, thus from B molecules, C molecules will form. That is the ultimate product. So if you draw schematically, if you draw a cartoon picture like this, so this is concentration y-axis and this is time at x-axis. So at first the initial concentration t equal to 0 will be just A0, no B and no C. So with time with rate constant Ka, the concentration of A will decrease. This is concentration of A, let's say. And then with time, with rate constant Ka, from A molecules, B molecules will form, right? So ultimately B molecules will form. But after a certain time, after forming some B molecules with rate constant Kb, from B molecules, C molecules will form. So basically then B molecules, the concentration of B molecules will then decrease again. Then with the decreasing of concentration B molecules with rate constant Kb, the C molecules will form. So ultimately if you draw the C molecules plot, it will look like this. So this is C. and this is, let's say, B. Okay, so at certain time, let's say this is T max, the concentration of B is highest, right? After then it starts to decreasing. So at we have to find out the T max here. So this is just for sequential or consecutive reaction, remember this. So the picture, the figure here is not correct here. So this is a kind of parallel reaction, but this T maxima will happen for sequential or consecutive reaction. And there is a formula for T max. There is an expression, we can derive that expression. So basically T max will be 1 upon, let's say, Kb minus Ka ln Kb divided by Ka. So this is the expression for T max, like time at which the concentration of B is highest or maximum. So so here in this question it is mentioned that the Ka equal to 2 Kb, which will be equal to 0.1 second inverse. So Ka is basically 0.1 second inverse, and Kb is equal to 0.1 divided by 2 second inverse, right? So Kn and Kb both are mentioned here, so you can find the T max from by just putting this value in this expression. Okay, so this plot is actually very important. So for consecutive reaction at T equal to 0, the only concentration is A. So this is the initial concentration of A0. Then with time the concentration of A will decrease, and then with rate constant Ka, from A molecules B molecules are forming. That's why the concentration of B gradually starts to increasing. Then after a certain time, from B molecules with rate constant Kb, C molecules are forming. So that's why the concentration of B molecules starts to decreasing, and then the concentration of C molecules increasing. So that's why a maxima kind of happening at this time. So this is T max. So maximum time at which the concentration of B molecules is maximum. And the expression for this is T max will be equal to 1 upon Kb minus Ka, and the general expression is, so basically T max equal to 1 upon K2 minus K1. So this is A, B, C, this is K1, this is K2. So 1 upon K2 minus K1 ln of K2 divided by K1. Okay, so this is the general expression. Okay, now let's move to the next question. So this is, the plot is given here with concentration versus T hub. T hub means hub life period, the time required to actually decrease the concentration of initial reactant by half, by 50%. So this is the half life period. So this is concentration and this is T hub. So let's say initial concentration of any reactant is A0, then at T hub the concentration of reactant A, let's say A T hub, will be initial concentration, so it will decrease by 50%. So initial concentration divided by 2. T hub means this. So time required to reach from A0 to A0 by 2 is called the half-life period. So here the plot is given, and at T hub equal to 2, the concentration is, or you can say at concentration 4 molar, the half-life period is actually 2, and if you decrease the concentration by half, that means 4 to 2 molar concentration, the T hub actually doubling, so 2 to 4. So you are decreasing concentration from 4 molar to 2 molar, then your T hub is actually gets doubled from 2 to 4 minute, right? So we have to find out from this plot the order of the reaction. So what do you think it will be? Anyone? No. So actually you have to just remember the expression for the half-life period with concentration, initial concentration or concentration of the reactant for different order of the reaction, like for zeroth order reaction. So okay, let me just revise that. For zeroth order reaction means, so rate actually depends the zeroth power of the concentration, right? That means the rate of the reaction, which will be dA dt, which will be equal to some rate constant, let's say times a to the power 0, right? So that means, so minus dA dt will be just k. Okay, so you can integrate that. So d of a minus equal to k dt. So initial concentration was a0 at time t equal to 0, and you are integrating up to time t, then concentration will be at. So after integration, so it will be just minus of at minus a0, right, equal to kt plus c or kt. You are just definite integration you are doing. So then minus of at plus a0 equal to kt, then at will be equal to a0 minus kt. So this will be the concentration relation between the concentration of the reactant A with time t with the rate constant k. So you can just plot here. If you just plot at with time t, then the plot will look like this, look like a straight line, decreasing straight line, right? So this will be the initial concentration a0, the intercept. So the plot will look like y equal to mx plus c, right? So c is the intercept, so c is a0 here, and m is negative. M is the slope of the straight line and it is negative, so that's why it is decreasing, right? Obviously the concentration of A will decrease, so that's why it is decreasing with rate constant k. So slope is actually k. So this is the concentration plot for zeroth order reaction. And you can also compute from this expression. So at t equal to t hub, then the at will be equal to a0 divided by 2, right? So you can just put at value, a0 divided by 2 will be equal to a0 minus k t hub. Okay, so it will be just k t hub will be a0 divided by 2, so t hub will be equal to a0 by 2k. So this will be the relation between the T half, that means half-life period, with the initial concentration. So you can see for zeroth order reaction the relationship is actually proportional, right? So if you increase the initial concentration, then the T half will also increase. Like if you double the initial concentration, the T half will also get doubled. But here in this plot we can see that if the concentration, so here concentration is decreasing for 4 to 2, but the T half gets doubled from 2 to 4 minutes. So actually inverse relation, right? So you can also write down the expression for first order reaction like this. So for first order reaction, I am just revising this, so it will be important. So first order reaction, the rate of the reaction will be minus dA dt, which will be equal to some rate constant time the first power of the reactant concentration, right? So you can, after integrating this, you can just get AT will be equal to A0 times exponential minus KT. So this is the concentration relation for the first order reaction, and if you just plot this AT with time t, then there will be an exponential plot. Okay, let me just check if I lost or not. Okay, good. So it will be an exponential plot at time t equal to 0. So it will be A0. Then with time t, so the concentration of A will decrease exponentially. So this is exponential in nature. For zeroth order reaction, it was decreasing by straight line. Now it is exponential. And at t equal to T half, AT will be equal to A0 divided by 2. You can just put this value here and compute the expression for T half. So T half for this case will be 0.693 divided by K. Okay, now look at this. So for first order reaction, it is important. First order reaction, the half-life period is actually independent. Half-life is actually independent upon the reactant concentration, right? So there is no expression of A0 term here, right? So that's why it is just the 0.693 divided by rate constant. So that's why it is T half is independent upon the reactant concentration is A0. So this is important. So for zeroth order reaction, T half is proportional to reactant concentration A0. For first order reaction, T half is independent of reactant concentration A0, right? It is independent. Now for second order reaction, so second order reaction, rate of the reaction, which will be minus dA dt, will be K s to the power 2, right? Second order. If you just integrate this, so you will get 1 upon AT will be equal to 1 upon A0 minus KT, like this. And your second order reaction, your T half will be inversely proportional to 1 upon reactant concentration A0. Okay, so for second order, this is for second order reaction, T half, that means half-life period, is inversely proportional to the initial concentration of the reactant. So remember this plot. So here the concentration is decreasing for 4 to 2, that means it is decreasing by 50%, and simultaneously the half-life period gets doubled from 2 to 4. That means here half-life period is actually behaving like inversely proportional to the reactant concentration, right? So that's why the order of the reaction will be 2 here. This is the second order reaction. Okay, is it clear now? Okay, so I'm hoping it is clear. Okay, so for the reaction A plus B to C plus D, delta H is mentioned here. Okay, A plus B to C plus D, delta H, which is the enthalpy difference. The activation energy of the forward reaction is 85 kilojoule per mole, and the activation energy for the reverse reaction. So we have to find out the activation energy for the reverse reaction. Okay, so just plot these ones. This is reactant, this is product. So this is A plus B, product is actually C plus D, right? So for forward reaction means reaction is happening from reactant this side to product this side. Reaction is happening by this way, reactant to product. So for this step the activation energy will be, so reactants have to climb this up to convert into the product molecules. So the forward reaction activation energy will be this much, EF. Now reverse reaction means from product P molecules P to R. That means reaction is happening this side, right? From P to R, reverse reaction. So the product molecule has to climb this amount of energy, right? So for this step, so that's why the reverse, for reverse reaction the activation energy will be this amount, ER. Now the enthalpy difference, now delta H will be E forward minus E backward. So this is the relationship we have to just remember. So difference in enthalpy is equal to the forward reaction activation energy minus backward reaction activation energy, or reverse reaction activation energy. So delta H is given, forward reaction activation energy is given. We have to find out the activation energy for the reverse reaction. So delta H is 2 kilojoule per mole. Forward reaction activation energy is 85 kilojoule per mole. Minus, we have to find ER. So ER will be just 85 minus 20 kilojoule per mole. So 65 kilojoule per mole. So option D, correct answer. So basically in this question you have to just remember the difference between the activation energy of forward and the reverse reaction is equal to the difference of enthalpy. Okay, so delta H is basically the EF minus ER. Okay. So in this question, so if A reacts to form either B or C according to the reaction A, okay, I'm just writing this. A to B is happening with rate constant K1, or A to C is happening with rate constant K2. That means it is a parallel reaction. Okay, from A to B, then A to C, rate constant K1, rate constant K2. So E1 is the activation energy for the first reaction. So activation energy for this reaction is actually E1, and activation energy for this reaction is actually E2. Then the observed activation energy for the disappearance of A, like for the total reaction, that means from A both B and C molecules are forming with different activation energy and with different rate constant. So you have to find out the total activation energy for the total reaction, that means the overall activation energy for the disappearance of A. Okay, so you have to find out the overall activation energy. Okay, so K1 will be equal to A times, we know the Arrhenius relationship, minus E1 divided by RT, and similarly K2 would be equal to E times E2 divided by RT, right? So if you just take logarithm of both sides, let's say from this is equation 1, this is equation 2, and from equation 1 if you take logarithm, ln K1 equal to ln A minus E1 by RT. So it will be equal to E1 will be equal to RT square del ln K1 by del T. Okay, similarly from equation 2, the activation energy for the A to C step, that means E2 will be equal to just RT square del ln K2 del T. Now for overall reaction, like overall disappearance of A to B and C, for overall reaction you can let's say the activation energy is E. So for overall reaction E, you can write E will be equal to just RT square del ln K1 plus K2, so overall rate constant K1 plus K2 del T. Okay, now we can just compute this. So it is RT square del ln K1 by del T. So then it will be so you can just take compute the derivative here, like it will be, you can just let me do this. So okay, so finally after doing the derivation, you can just get E will be equal to just K1 E1 plus K2 E2 divided by K1 plus K2. Okay, so this is also an important relationship. So basically for parallel reaction, any parallel reaction, let's say from A to B, then A to C, then A to D, so let's say it is K1, this is K2, this is K3, activation energy is E1, activation energy is E2, activation energy is E3, like this. So for this, the overall reaction, for overall disappearance of A, the activation energy, let's say E, so E will be equal to just K1 E1 plus K2 E2 plus K3 E3 divided by K1 plus K2 plus K3. So this will be the general relationship. So for this case it will be just K1 E1 plus K2 E2 plus K1 plus K2. So option C will be the correct answer. Okay. So the following reaction was carried out in water, which is the Cl2 plus 2 minus 2I minus 2I2 plus 2Cl minus. Okay, so the initial concentration of I2, this will be I2. So initial concentration of I minus, so initial concentration of I minus was 0.25 mole per liter. Okay, let me just write it. Initial concentration of I minus equal to 0.25 mole per liter, and the concentration after 10 minutes was 0.23 mole per liter, and after 10 minutes it will be 0.23 mole per liter. And the rate of disappearance of I minus and the rate of appearance of I2. Okay, so after 10 minutes, the decrease of the difference between the concentration of I minus is, so basically okay, let me, so T at T0, the I minus concentration initially was 0.25 mole per liter. Now at T10 the I minus concentration is 0.23 mole per liter, so it is decreasing obviously because the reaction is happening now. So delta, the difference between these two concentrations, so delta of I minus by delta T, right? So delta of I minus means I minus at time t equal to 10 minus I minus at t equal to 0 divided by T10 minus T0. So it is 0.25 minus 0.23 divided by 10 mole per liter, and this is minute. So 0.02 divided by 10, right? So 0.002 mole liter inverse minute inverse. This is the unit. Now we have to find out the rate of disappearance of I minus and the rate of appearance of I2. Okay, let's write down the chemical reaction again. So Cl2 plus 2I minus 2I2 plus 2Cl minus, right? So for this reaction, if you write down the rate of disappearance of I minus which will be half of, because 2 is the stoichiometric coefficient of I minus, so rate will be half of d I minus dt. So this will be the rate of disappearance of I minus, and the rate of appearance of I2 will be just d of I2 dt, right? Because the stoichiometric coefficient of I2 is 1, so it will be equal. So the rate at which the I minus is disappearing and the rate at which the I2 is appearing, it will be equal, right? So d of I2 times dt equal to half of d of I minus times dt. Okay, so we know that the d of I minus times dt is equal to 0.002 mole liter inverse minute inverse. And the rate will be, so this is delta, so rate will be equal to, so this is the di minus time dt, and the di2 time dt will be rate of appearance of I2 half times 0.002. Okay, so it will be equal to 0.001 mole liter inverse minute inverse. Okay, so main thing is the rate at which the I2 is appearing will be equal to the 1 upon the stoichiometric coefficient of rate at which the I minus is disappearing, right? So this will be the main expression. Then why I am doing it, because after 10 minutes, so concentration of I minus is decreasing, so we can take the difference between the concentration and we can divide with time, then we can get the di minus dt, right? So that's why I am doing this. So that is basically means the di minus dt derivative. Okay, so is it clear, or you can have any doubts?
Clear, sir.
Okay, great. So today I'm just ending here now. So in the next class we will be solving many questions. Okay, so if you have any doubts you can ask, or otherwise I will end today.
Okay, sir. Thank you so much.
Okay, so see you in the next week. Okay, bye.
Yes, sir.
Bye.